Hey, Dr. Clark coming back at you with another example video here. This time we're looking at Laplace transform, some advanced examples using unit step functions, forcing terms coming on and off, as well as the translation theorem. So let's take a look. The first problem here is a spring mass problem. So we've got a 32 Newton weight that will stretch a particular spring 2 meters. And then we have a 1 kilogram mass released from rest from the equilibrium position, and they want us to find the equation of motion x of t if an impressed force of 20 t newtons is acting on the spring only from 0 to 4 seconds and then is removed. Ignore any damping forces. Okay, so your basic mx double prime plus bx prime plus kx equals f of t, that's the standard damped harmonic oscillator differential equation, second order. They tell you that the mass is 1, so that's going to be just x double prime. They tell you to ignore any damping forces, so that's going to be 0. And then they tell you that the spring is stretched 2 meters under a 32 Newton force. So if you've got 32 Newtons being balanced out by a motion of 2 meters, well, then K, the spring constant, must be 16 because 32 Newtons will pull it 2 units, at which point the restoring force is balanced with the external force of 32. So we've got 16x. All right, equals right-hand side f of t. Now, f of t is the external force, and they're telling us it's 20 t newtons. So the force gets stronger and stronger and stronger until after 4 seconds, it's up to 80 newtons, and then it is removed. So you're kind of pulling, 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 and then release that force, and then we want to see what is the effect of that on the equation of motion. So this is really 20 t. That's if it was just 20t forever, but we need to turn off that 20t. So the way to do that is actually to subtract 20t times the unit step function u t minus 4. And the effect of that is going to be, for the first 4 seconds, that motion is going to go up until eventually it will reach 20 times 4 is, I guess, 80 newtons of force. And then it's released and it'll go back down to 0. Okay, so when that is released at t equals 4, ut minus 4 becomes 1, and so 20t minus 20t becomes 0. Before t equals 4, u is 0, and so you just get 20t. So it goes from 20t to 0. All right. The problem is that we cannot solve this differential equation as written because when you do a unit step function from the translation formula, it has to be of the same translation. So we need not t, but t minus 4 to match up with ut minus 4. The that slide has to show up in the t function as well in the exact same way. Here and here has to be t minus 4 with t minus 4, and it's not written that way. But we can fix that. And the way we fix that is we just note that t is equal to t minus 4 plus 4, right? T minus 4 plus 4 is t. So everywhere I have a t, I could just replace that with t minus 4 plus 4. Okay, so I'm going to subtract 20, and then what did I just say t was equal to? T minus 4 plus 4, and that's still going to be multiplied by u t minus 4. So that little substitution, I've not changed the equation at all. I've just substituted in t minus 4 plus 4 for t. But if I then multiply this ut minus 4 into that, then what I will get is a formula that's in the right form. So 20 t minus 4 u t minus 4, and then minus 80 u t minus 4. So you can see here 20 times 4 is 80. With the minus, it makes it negative. And then here's just the negative 20 times the t minus 4. And so that's just explaining that there. So now I've got just a basic function here. I've got ut minus 4 multiplied by t minus 4. So that's matched up good. And then here I've got ut minus 4 times the 80 function. Now there's no t in it, so when you slide a constant function over, it doesn't matter. So that's going to be just fine. And all we need to do then is to solve this differential equation right here. Let's copy that, paste it onto the next page, and let's start solving it. So how do we solve it? Well, we take the Laplace transform of the entire thing. And so we're going to get S L of x prime minus x prime at 0 plus 16L of x. That's going to be 20 times L of t. It's going to be minus 20 times L of this t minus 4 u t minus 4. And then minus 80 times L of u t minus 4 times the 1 function in this case. Okay. Now, we got a lot of work to do here, but the first thing was it did say that it was released from rest at the equilibrium position. So to me, that means x prime is 0 and x is 0 at t equals 0. So in particular, that's going to be 0. And now we're going to get s times s L of x minus x of 0, but that too will be 0, plus 16L of x. So if you don't mind, I'll just do the left-hand side here. We're going to get s squared plus 16 times L of x on the left-hand side. Okay, now on the right-hand side, we've got this 20 times L of t. So let's tackle L of t. What is L of t? I believe that's 1 over s squared, right? So that's 1 over s squared. And then we're going to have minus 20, and I need to do this part. Okay, so it's L of t minus 4, u of t minus 4. Okay, and so what happens there is from the second translation theorem, we basically just say we're translating at 4 units. So we just get e to the minus 4s times by L of the basic function. And so t minus 4 is the function t translated by 4 units. So I'm going to multiply e to the minus 4s times L of t. That's what the translation theorem says. And then I'm going to have minus 80. I've got a shift of e to the minus 4s. And then I just need L of 1. Again, this is really the 1 function that's been translated by 4 units. So I get the translation e to the minus 4s and then L of 1. And I should know what these are now. So s squared plus 16 L of s is going to be 20 times 1 over s squared minus 20 e to the minus 4s. L of t is also 1 over s squared. And then 80 e to the minus 4s times L of 1, and that's just 1 over s. And then L of x would be what we get when we just divide everything by left-hand side s squared plus 16, which is the characteristic equation for an undamped harmonic oscillator. So that's another thing you want to pay attention to, is right here you always see the characteristic equation. S squared plus 16 minus 20 e to the minus 4s times 1 over s squared plus 16, and minus 80 e to the minus 4s times 1 over s times s squared plus 16. Okay, now there's going to be some partial fractions we've got to do here. So let's take a look at those first. 1 over s squared plus 16 is the first one. That's going to split up into a over s plus b over s squared plus c over s. No, sorry, that's an irreducible quadratic. So cs plus d over s squared plus 16. Okay. So that's just the standard partial fractions formula. And if you want, you can run this in Wolfram Alpha. It'll do it for you. But we'll do it by hand just for fun. Let's clear out the denominators. Multiply everything by s squared plus 16. That's going to give us this. And we should be able to get some of these for free if we think through it a little bit. For example, if we just take s equal to 0, that gives us something. It gives us 1 equals b times 16, right? Yeah, of course. Yeah, because this is 0. That's going to be 0. This will be 0, so it's just 16b. So that's going to imply that b is 1 over 16. I'd like to do that trick again, but I can't really do any other ones because s squared plus 16 is, doesn't have any real roots. So the rest of them, I think I'm going to have to do the standard method of just multiplying everything out. So in particular, I could look at, let's see, we've got 1 is going to be as cubed plus 16as plus bs squared plus 16b, cs cubed plus ds squared. And then let's just take them one at a time. First, let's take the cubes. There are 0 cubes on the left-hand side. There's as cubed, and there is cs cubed on the right-hand side. So that's one little thing we know. If we look at the squareds, we're going to have 0 squareds on the left-hand side and, 1 over 16 s squareds. And then ds squareds. So d must be negative 1 over 16. Okay, so that's nice. And then what else could we do? I guess we could look at the constant term. Yeah, the b's we already did. That gave us the constant term. Is there a linear term? Yeah, there is a linear term. In fact, if you look at the s's, I'm getting 0 s's, and that's got to be equal to 16 a s's, right? But that should tell you that a has to be 0. And that would also tell you that c would have to be 0. So do we just have a b and a d in this case? I think so. I think this is all reducing down to 1/16 over s squared plus d, which is negative 1/16 over s squared plus 16. So there you go. That's kind of a nice reduction there. All right. Yeah, and I guess if you multiply that out, you're gonna get exactly 1 over s squared plus 16. So that's nice. Okay, so that's that one. Okay, what was the other one we needed to do? That's the first two. Oh, we have 1 over s times s squared plus 16. So let's clear out 1 over s times s squared plus 16. So that's going to have to equal a over s plus bs plus c over s squared plus 16. That's, of course, the same irreducible quadratic. Clearing out the denominators, we get a s squared plus 16 plus bs plus c times s. Okay, we should be able to, setting s equal to 0, get one freebie. Yes, 1 is equal to 16a, so a is 1 over 16. And then we could look at the s squared terms. So there's 0 s squared terms, but that's as squared plus bs squared. If we just look at the s squared terms, but we already know that a is 1/16, so that implies that b must be negative 1/16 because there's no s squareds on the other side. Now we got b. And how are we going to do c? Well, there's, I believe, 0 s terms and then cs on the other side. So c must be 0 in that case. Otherwise, you can't get the s's to cancel out. All right, so in this case, this is going to reduce down to 1/16 over s plus negative 1/16 on s over s squared plus 16. Okay, so putting these two things together, we're going to have L of x, that's left-hand side, equal to this. Let me just copy this one more time here. and paste it down. Oh, no, let me go back. Let me paste just the text here. There. Okay, so this is going to equal 20 times what we just figured out for s squared plus 16, which was 1/16 over s squared. And then negative 1/16 on s squared plus 16. Okay, that's the first term. And then we're going to have, well, let's see. I'm just going to write a big plus here. And if you don't mind, I'll factor out a negative 20e to the minus 4s. Okay, so that's going to give me, I guess I factored out this and this, but I will have a minus 4 on that second term there. But this one is the same. It's 1/16 times 1 over s squared plus negative 1/16 times 1 over s squared plus 16. And then we're going to have plus 4 times, and with this is 1 on s squared plus 16. So that's going to reduce down to 1/16 s, or 1/16 1 over s, plus negative 1/16 times s over s squared plus 16, parentheses and bracket. Okay, so that's what L of x is in this case. And then we should be able to then essentially what? Well, I guess we could combine like terms if we really wanted to. Well, there's not too many like terms, is there? And in fact, there's no like terms because this is s squared, this is s, that's s over, and that's 1 over. So yeah, we don't have any like terms in this case. Okay, so now we're essentially ready to figure out what x of t is using inverse Laplace transform. So first we have 20 over 16 times what gives you 1 over s squared? Well, that's the t function, isn't it? Yeah, t gives you 1 over s squared, so that's just going to be times t plus negative 20 over 16. So here's 20 over 16 negative. That's that. And then what would give you 1 over s squared plus 16? Well, s squared plus 16 sounds to me like sine of 4t. The only problem is the sine formula has a 4 in the numerator. So I actually need a 4 up there, which means I'll have to divide by 4 because you can multiply and divide by 4. So really, instead of having 4 over 16, I'm going to have 4 over 64, or negative 20 over 64, which is 16 times 4. And then this will become sine of 4t. Okay, so that's the first two terms. Now, the rest of this is going to be, so plus, when we have this e to the minus 4s, that's telling us that everything is going to be shifted to t equals 4. Okay, so what I should get is the basic function corresponding to each of these differential equations, but shifted by 4 units. Okay, and multiplied by ut minus 4. So I'm going to have negative 20 u t minus 4 times whatever would land on this, but then translated 4 units. So what would land on s squared? Well, that would be t, right? So this is going to be 1 over 16 times the t function, but it's going to be t minus 4. It's the shifted t function. Okay. Then I'm going to have negative 1 on 16 here. So there's the 1 on 16. This is also coming from sine, but it's going to be a shifted sine function. But I'm also going to need the 4 there, so I'll need a 4 on the denominator. So instead of having 16, I'm going to have 64 again. And then I'll have a sine of 4t, but that t is going to be shifted by 4 units. Okay. Then I've got what? 4 times 1/16. So that's basically a fourth. And then 1 over s is the constant coming from the constant function. So it's just basically 1/4. So that's just 1/4. And then you might wonder, well, how do you shift t to t minus s? Well, there's no t's, so there's nothing to shift. If you shift a constant function, nothing happens. It just turns on at 4 seconds right here. So we've handled that term. And then this is the last one to handle. Although, ooh, this one's a little bit messy. Let me pull this onto the next slide and let's just work it through, and then I'll write it in here. So we have negative. Yeah, so we basically have what? If we take this 4 and the negative 1/16, that's negative 1/4 s squared plus 16. So I've got negative 1/4 and then s. No, that's fine. Yeah, there's nothing to there's actually, whoa. There's nothing to worry about there. That's just cosine. It's actually in the right form for cosine. I'm sorry. I was thinking it was a little bit messy. But it's not. It's just plus negative 1/4. And then it's going to be, I can't squeeze that down there. So plus negative 1/4 right here. So there's the negative 1/4. And then that looks like it's coming from cosine. So cosine of 4t, but I just need to shift it by 4 units. Cosine of 4t shifted, 4 t minus 4. I got to shift that cosine function. And then I bracket that. And that is the solution. So you end up with sort of the initial response to the forcing plus a homogeneous solution to kind of get the initial conditions set up correctly. And then you've got this, which is going to turn on, right? You're turning on at 4 seconds. Well, what's really happening is you're turning off the forcing term. And so the other solution would propagate up if you didn't do anything. So now we have to depropagate it, which is what goes on there. So hopefully that was helpful. It's kind of a nice problem to see, you know, how can you actually solve one of these harder, you know, spring mass problems with all of the trappings of, you know, right-hand side forcing that turns on and off, as well as, you know, partial fractions and all that good stuff. So we'll see you in the next video, and I hope this was helpful.